Hi everybody. Today we're going to talk about a common malware technique where you resolve an API address by hash instead of by function name. We're going to start with a little bit of time on the academic background to understand the topic, and then we'll walk through a few examples in order so we can recognize the technique in assembly code. So to start with, let's go into the background of how APIs are resolved. There's two different ways you can do this. You can do it at load time or at runtime. If you do it at load time, this is using the import address table, and this is where the loader resolves in an initialization code prior to reaching any actor written code. Runtime resolution is where the actor writes code that actually resolves the API addresses after the loader maps the file into memory and when you get into the actor written code. So really the only big difference is the load time resolution is done by the compiler automatically, and the runtime resolution is done by the actor and written code. So there's two different ways that we can resolve APIs at runtime. We can use APIs, this is with load library and get proc address, or we can walk the portable executable header, specifically the export address table or EAT. So you may be wondering, if you can use a API like get proc address, why would you ever want to walk the PE header itself? There's two reasons for this. The first is that the APIs aren't loaded, so you can't call them. This is the case in shellcode. The second is for general obfuscation reasons. If you use an API like getProcAddress, you have to pass the function name as an argument. That means there's no way to obfuscate which function you're resolving. AV scanners will know the APIs you're using, Malware ANOS will recognize it. There is just no way to hiding it. So if you want to obfuscate it to make it a little bit harder to identify the capability, you can do it manually by using the hash. In this case, you're basically going to walk the PE header, walk an arrays of all the names and hash them, and then compare it to your target hash. And then once you find it, you'll resolve the API address manually. So this way, you just don't have any indicators that can be quickly pulled out through strings or through other methods. So there's three typical use cases that use this method: shellcode, packers, and then just general AV avoidance or obfuscation methods. So now that we know a little bit about the background, let's step into the algorithm itself. Because the algorithm goes into walking the PE header, let's discuss what the PE header is just real briefly so we have a little bit of context. This is a basic diagram of the PE header. The header is basically just a combination of structures that has information about the loaded file. So you start with the DOS header, and this has the MZ signature at the beginning and a field called the ELFA new that we're going to talk about, and this field points to the start of the NT header. The NT header is a structure with multiple child structures. You have the file header structure and the optional header structure. Inside the optional header structure, there are more children structures, basically called the data directory structures. The structure we're interested in is the first data directory, and this is the export data directory. And this is going to contain the export table entry that has the export address table, which has all the exported function names as well as the addresses. So basically, the algorithm is going to walk this PE header, get down to the export data directory, follow that to the table entry, and then walk the array of exported names, hashing them until it finds the correct one. And what it does is it's going to return the address. That's all we'll really do it. But to see that a little bit more formally, let's write out these steps so we can recognize it. And it's a relatively simple algorithm. The first thing we want to do is find the NT header. After we find the NT header, we want to find the export data directory. From the export data directory, we're going to identify the current API name. Once we have the API name, we'll hash the name. And then finally, we're going to return the API address in memory. And that return value is where it's loaded in memory, and that's what you use to call it. That's all getProcAddress does, and that's all we're going to be doing manually. So there's a couple different ways we want to be able to recognize this. We want to do it by context and by instructions. Context is the easiest way, and when you have a separate function that performs this, we'll call it getProcAddress by hash. It's relatively simple to recognize. If you see a function where you pass two arguments, and the second argument is a large hex value, which is the hash number, and the return result is called, and then possibly stored in a D word like a global variable, or a structure and later called, then that's basically the getProcAddress by hash, and that's all you need to look at. You know it's resolving an API because the return is called. and then the fact that you're passing a hash value tells you you're resolving it by hash. Fortunately, when you have a standalone function that resolves the APIs by hash, it's almost always the only functionality included in the function. You very rarely see it included with like a dual use function. But just to be sure, we could step inside the function and look at the individual instructions, and we want to be able to recognize these steps. That will kind of confirm that there's no additional information that you need to reverse in that function. The second way to recognize this is to recognize the functions or the individual steps. And you want to be able to do this because the function won't always be a standalone function. Oftentimes the compiler will inline it. That means they'll take the instructions out of the function and put them in line with the rest of the assembly instructions. So there'll be no call to a separate function to recognize by context. This is often the case in shellcode and actually packers too. So very generally, if you do it for AV avoidance, it will often be a standalone function, and shellcode and packers will often be as an inline function. So luckily to recognize this, it's actually pretty simple. We're going to look for a number of offsets. And these offsets are pretty unique in code, and so once you see the offsets, you'll know that you're looking at these steps. But I want to make sure, we need to be clear that these offsets are constants we're looking for, not stack variables. So if you're looking inside a disassembler like Ghidra or IdaPro, it's pretty simple to recognize. The constants will be standalone and they're separated from stack variables or arguments. But if you're looking inside of a debugger, you don't differentiate between constants and stack variables, so in that case it's a little bit harder. So I pulled up just from Google the PE specification, and most of these values I'm going to talk about are from the export table entry. So I'm just going to scroll down into here and look for the export, and we can see we have this eData section. This is for the export, and after we start parsing the header, we're going to be looking for this export directory table, and there's three entries we're looking for. We're looking for the this export address table, the names array, and the ordinal array. So basically you have the address array, names array, and ordinal array. These are the three main offsets for getting the return API. These are all going to work in conjunction in a little bit of a convoluted manner. Exactly how they work together is not all that important. We're just looking for the offsets. But just a little background. Basically what you're going to be doing is walking through the names array, hashing each name. When you find the appropriate name, you're going to take that corresponding index out of the ordinal table. You're going to dereference that ordinal table to get another index. You're going to bias based on this ordinal bias base, and then you're going to take that index out of the address array, and that'll be your return value. The other thing to note is that all these pointers are basically relative virtual addresses, or RVAs. So you're often going to see in code these RVAs converted into a full virtual address. All that is adding the RVA onto the image base. What that looks like in assembly is you'll see the return result from here added to another register, and that register contains our image base. So again, not super important to recognize all the steps, but the more you recognize, the less ambiguity there is, and the more confidence you'll have. So now that we kind of had a little bit of that background, let's go into what the offsets are. So finding the NT header, this is looking for the ELFA new field we talked about. This is going to be a register plus hex 3 Charlie. And that register will basically be the image base of the loaded DLL or the MZ signature. Once we find the NT header, we're looking for the export data directory. And this is going to be the register plus hex 78. And from this register is going to be the NT header. So basically the result of this ELFA new added to the image base will be this second register. Once we have that, we go into the API name. So this is grabbing out the names array. And this will be a register plus hex 20. If we look back at our table here, the specification, we see this names point array is at decimal 32, which is hex 20. Now we're going to hash the name. And so for here, we're looking for the API name as arg to function with math instructions. This is just a little bit by context. And we want that in the relative location after we resolved the API names. And finally, we're going to return the address in memory. And this is a register plus hex 1 Charlie. And again, we come back to here and we see the address table is the 28, which is hex 1 Charlie. So those are all the steps we need in order to recognize this as the instructions, and then we talked about the context. So you can either see it by context and then step in to verify the instructions, or if it's inline, you can just look for the instructions. The one thing to note is we don't necessarily have to recognize every step. If you see a function or the start of code that has the 3 Charlie and the 78, that immediately tells you you're walking the export data directory and you're going to be resolving an address. All the code in between that steps and this final returning the result is basically utility code that's doing these individual steps. And so because this isn't usually put with other functionality, a lot of times you can just scroll down until you find the reg plus 1 Charlie to find the end of it. So if it's inline, that can tell you kind of the start and the finish. And if it's a separate function, that will just kind of verify the full functionality. And then you don't usually have to worry about what's in the middle. Again, the more understanding you have, you can scroll through it to make sure there's nothing there, but 98% of the time, it's going to be a standalone function. So with that, the last thing we want to talk about is basically the methods to resolve the API hashes. Recognizing that you're doing a get proc address by hash is important, but really you need to resolve the API address to identify the malicious capability. There's 2 different ways we can do this. We can do it dynamically, or we can do it statically. I'll talk just briefly about the pros and cons of each. So dynamically, the pros is it can be quick and minimal understanding is needed. All you need to do is run a debugger over the function and look at the return result, and if it's an API call, your debugger will resolve that and will basically show the name in memory. So you don't have to know how it's working. All you have to do is step over it and see an API address probably in the EAX register, and you know what it did, and you know what API it resolved. The cons is it modifies the binary. That means if you want to save off these names, you need to save off basically a dirty copy of the file, or need to manually copy those return addresses or return function names into a clean database, so it can take more manual methods. It can also be difficult to reach all target functionality. If you're lucky, it'll be on the main code path, but oftentimes it'll be spread throughout the function, and it can take a while or just be difficult to find all of them. And finally, you have to replicate this for every file. So if you're doing it one time, it can be, maybe it's not too long, but if you have to do this for 20 variants, the time really starts to add up. Static analysis is through scripts. This has a number of pros. It can be very quick to run on variants. Once you have the script written, oftentimes you can run it immediately on variants or with a very small modification. The script also serves as analysis notes. So that means you can put it in reports, you can share it with other researchers, and it will document basically how the function works. So it'll document the hashing function, it'll document which function is calling or doing the get proc address by hash functionality. So it saves as a good, just good note taking. The cons is basically it requires more time up front and more education to be able to do it. You need to be able to know how to script in your different tools. You need to be able to reverse engineer the hashing algorithm. So it takes more experience, to be able to do that. And then it also takes more time because you have to build the script initially and do the reverse engineering. So basically, more upfront time to build it, and then the more you use it, the less the time comes. The dynamically is less time upfront, but the more you do it, the more the time adds up. So for this video, we're not actually going to resolve the API addresses. We're just going to go over examples of how to recognize it. And then in the next video, we're going to go through kind of a modification of the dynamic and static analysis. I'm going to provide you with tools where you can run the debugger to resolve the API addresses. And then instead of saving off that binary where it's kind of modified, we'll show you a script that will take the names and copy them into a Ghidra database. And then you could always port the script over to IDA or any other tool you use. So that kind of gives you the both of both worlds. You don't need a lot of experience to start using it, and you can do it relatively quickly, and on variants will be a little bit quick. So that's all the kind of background we need to talk about. So let's walk into a couple examples to see how this looks in assembly code. So all these examples, the hashes are in the video description. You can download them with Malware to practice on your own. Let's go to our first example. So for the first example, I'm going to hit G to go, and this is that address 403 echo 40. So I'm going to hit the graph view, and then give Ghidra a second to redraw it. I just like the graph view because it's easier to see the control flow as I walk through this. So I'm just going to start scrolling through, and I immediately see a hex 3 Charlie here. And because this is a constant, I know I'm parsing the NT or the PE header, and I see that's an EAX. And then I add to that hex 78. So I have the 3 Charlie and 78. I immediately know this function is going to be resolving or walking the export data directory and basically resolving an API address. So now I want to watch the other steps to see how it's doing it. I scroll down here. I see a 1 Charlie, a 2 0, and a 2 4. So this one Charlie goes into EAX. I add it to a register. That means I'm converting the RVA to a VA, and then move that into local 8. So I hit L to rename this. I'm going to call this the address array. The 2.4, I goes in EX. Again, add to EBX, so I convert the RVA to a VA and move into local Charlie. At local Charlie, I hit L to rename. I'm going to call this the ordinal array. And then finally, we have our hex 20 that goes into EBP. Again, you see the conversion from RVA to VA. And I scroll through and I see, because this is the array of names, so it's an array of pointers to the string names, I'm basically dereferencing that into ECX, converting the RVA to a VA, and then it looks like I'm passing to this function as the first argument through fast call. The fast call is where we pass the arguments through ECX and EDX and then on the stack. So now I just want to step in this function and make sure it looks like a hashing function. So I'm going to step in here because I'm passing the string as an argument, and then I immediately see a bunch of math operations. So I see shift rights, ORs, XORs, adds with math constants. I scroll down. I see a loop with a bunch more math. So I see XORs, I see adds, I see big hex constants here, and then I exit out. So that's pretty clearly a hashing function. So I hit Alt left to get back to where I was at, and then I'm going to rename this. Hit L to label. Hit L to label. Call this hash. So now that we have our hash, we do a final XOR out of that, and then we compare that to local 10. If that's equal, this local 10 is likely our target hash. We come over to here and take the green path. And now we see the ordinal array and the address array. So this ordinal array we're grabbing out, we're adding that onto ESI, into EAX, and then adding that into ECX, which is our address array. So this couple steps here is where we're basically taking the ordinal array, biasing it by the base, and then taking that reference out of the address array. So that's a part you don't really need to recognize. It's just a little bit of background information. The fact that you see the address array coming out here, we dereference, we add to EBX, so we're converting it to from an RVA to a VA, and then we compare it to EDI. So basically, anytime when you get to this step, you'll have it compared to another value, and you generally want to take the jump less than equal to that. So we take this jump down here, and this is where you can see we're returning ECX into EAX and return. And just so you can see the ECX, this was a result of where we compared or converted the RVA to a VA. So that is the address array. So even though you see the summary view, the satellite view, there's a lot more functionality here. We're returning the address in memory. And so that means this whole function is get progress by hash. So we don't have to worry about all this other functionality. It's just alternate kind of code paths, error paths, things of that nature. So I'm going to go up here, and I'm going to hit L to label. I'm going to call this get proc address by hash. And I'm going to look at this context too, just for the final verification. So I hit Control Shift F to find the cross references. And then I'm going to just go to, let's go to this one in the entry code. So I'll select that, and then I'll close this down, and then I'll give Ghidra a second to redraw. And we see here, it looks like we're using fast call again. So in EDX, or the second register, we're passing our hash value. The result, we're storing in a dword, so a global variable, and we're also immediately calling it. So if we're looking at this top level, we'd immediately be able to see this is get proc address by hash, because we're passing a hash value, and we're calling the return result. And then if we want the extra verification, we could step into it and see the individual instructions in assembly that we just went through. You can see that's pretty simple. Let's go through a little bit of a more complicated example. We'll do this for the example 2. And this is actually a reflective DL loader, and this one's going to be inline. So I'm going to do the exports, and I'm going to label it for us reflective loader. And then I'm going to open up the graph view so it's a little bit easier to see. And oftentimes we get in unpackers like this, you're going to be inline, and that means it's going to be inline multiple times. You're going to be resolving several addresses. Oftentimes you'll resolve load library and get proc address, and then use those to resolve future ones. Just depends. So we're just going to walk through one example and to see what we're looking for. So here, we're just looking for the 3 Charlie. So I see a 3 Charlie here, but I don't see the 78. So I'm going to keep scrolling through. I'm just looking through until I find my indicators. So now in this code block, I see a 3 Charlie and I see a hex 78. So immediately I know I'm walking the export address table. So this is going to be the start of our get proc address, and then we'll verify it's by hash. It could be by another manner. You could literally just be looking at the name. You could be doing it by some other obfuscation method. It's just a hash is the most common. So we can see here, I see a 20 and a 24. So let's look at the 24 first. This goes in EAX. I convert my RVA to a VA by adding to ESI and store this in local 14. So I hit L to label, and I will call this the ordinal array. And then I see my 20. This is the name array, goes in EBX. Again, convert RVA to VA by adding to a register. And then I see I dereference that pointer here into EDX. And then I grab the individual byte into CL, and I go into this loop, which is basically our hashing loop. You can see this is relatively simple. It's just a roar by hex delta, and then we have an add, basically the hashing value. So this is our hashing loop, and we come out, and we can see our EAX is the add here. So our EAX is comparing to this target hash value, the echo Charlie, let's scroll through, echo Charlie, echo 4, echo 8, echo. So if that's equal to our hash, we take the green path and we come down to here. Now we see our ordinal array, and we see a 1 Charlie. And if you remember, the 1 Charlie is the address array. So we're dereferencing, taking the ordinal, rebiasing it, and then adding it into taking that index out of the address array, grab that into ECX. We're converting the RVA to a VA into ECX. And then you can see here, this is a little bit funny. We're comparing, again, EAX to the same hash value. So you see EX didn't change, and you see the hash value didn't change. So we know ECX is our target address in memory, and our EX is going to be equal because it was equal up here. We jumped if equal, and we didn't change EX, so it'll be equal again. And so we come down this green path. Oh, sorry, this is jump not equal. And because they are equal, we take the red path. And then we can see basically this is a pointer to the address array. We're going to dereference it into EAX. Again, everything's in RVAs, so convert RVA to VA and store that into local 1 Charlie. Hit L to label, and I'll call this resolved API address. And then we're going to take this jump down here. Let me double click that. We're going to take this red path, and we're not going to take the loop because we would be basically exiting out of here. We continue to follow this path, come down to here. Oh, I forgot this is the loader. So we can keep on scrolling through here until we find it, but because this is resolving more APIs, it's going to take a little bit to find. So let's actually walk back up to where we saved that, and we'll just do a little shortcut because sometimes it's a little bit difficult to find where that's going to call it. I think I went too far, so let me scroll down here. I see my 78, I see my hashing. All right, so here we were. So here's our resolved API address. So let me select it. In fact, check the cross references. Control-Shift-F. And now I see, this is used a couple times. So I see I zeroed out here. I store the resolved API address into it. And then you see here I have a call, and the call to that resolved API address. So that kind of gives me the confirmation that I did use it in the expected manner. Now, in this particular file, it's actually reused for, the stack variable is reused for another situation after you call the API. So that's why you're moving the ECX into it over here and then doing some more stuff with it. So in this case, it's a little bit harder to see without analyzing the whole unpacking function. So just seeing the call to the resolved API address is enough confirmation for us. So you see in this case, there was no function to recognize by context. We just had to see the individual steps, and then we could label the output. Let's close that down, and let's look at one more example. So this is example 3. So I'm going to type G to go, and for this one, I'm going to 41000, and then I'll open up my graph view to make it a little bit easier to see. All right, so I'm going to scroll down here, just looking for my indicators. So I see a 3 Charlie here, so that means as a constant, I'm parsing the PE header. And then I see a +78, a register +78. That means I'm parsing the export address table. And so I know I'm going to resolve an API address. I see a +20, 1 Charlie, and 2 4. So this +20 goes in EDX, and then we store that in local 34. I'll hit L to label, and I'm going to call this the name array. And then 1 Charlie goes in ECX and stored in local 24. Hit L to label, and I'll call this the ordinal array. And then finally the 24, sorry, this was 1 Charlie. So let me hit L to label that again. And the 1 Charlie is the address array. It's going to be hard to recognize if we label it wrong. The plus 24, that's the ordinal array. That goes in EAX and stored in local 20. So I'll hit L to label, and I'll call this the ordinal array. Alright, so now it's going to keep on scrolling through. So now I see my names array goes in EDX. I basically grab that value out into EAX, convert it from RVA to VA, move it to local 38, and back in ECX, and then as an argument. That means I'm passing the name pointer into this function. So I'm expecting this to be some type of hashing function. Let's step into it to verify. We'll step into the inger function too. Alright, so I'm just going to scroll through and look to see if it looks like a hashing. So I see an unknown function. Let's check that. So if I scroll through here, I see a loop. I don't see any hashing functions or math instructions. This looks like it's actually doing a string length, and we're not going to be worried about how to recognize this for this video. But let me hit Alt left to get back out, and I will just hit L to label and call that string length. At least on quick inspection, that appears to be it. So I keep scrolling through. I'm just looking for indicators. So I'm going to again step into child function, just in case it's done into that inger function. So this, I see a hex 41, 5A, and add with the 20. That means I'm doing a string to lower. And again, I'm just going to label this and not worry about how to recognize it for this video. This is just a background, so I'll call this to lower. Alt left to get back. So basically got a string length. We converted a string to lowercase. And now I see math instructions. So I see basically a loop here. We have this loop, and we have an AND with a big hex constant, which is often used in hashing functions, and an XOR here with EDX and EAX. So this is basically our hashing function. And then we come down here and we exit out. So again, it's a simple hashing function. There's not a lot of math instructions. You just have this one constant and an AND along with the XOR, but that's basically all we're looking for a simple hash. So I'll hit Alt left to get back to where I was at. And then we can label this as a hash. So I'm going to hit L to label and call this hash. So just the fact that we passed the string name into here and did a little bit of math instructions on it in the spot we were expecting it, then that tells me it's a hashing function. We bring out EX compared to the param2. So that's probably our target hash. If we are equal to that, we come down to here. And you can see here we're doing another check here, but we haven't with a 78. But we have the ordinal array. Convert that into the address array into ECX. Do our little bit dereferencing. And then we compare that to a local for Charlie. Remember, when we see the compare of the address to another value, just generally take the less than or equal. So we'll take the green path. Here we basically do the same thing, the ordinal array, the address array. So this is basically just, they redid the check instead of saving it off as a variable. And so we're doing the same thing. We're grabbing the ordinal, biasing it, grabbing the index out of the address array. That goes in EAX, add it to ECX. That means this local 18 is converted from a RVA to a VA. And this local 18, I can get L to label. I'll call this resolved API address. Now we're going to take this red path down here. So we're going to double click this. And then we take this jump, double click it again. And we see the resolved API address goes into EAX. We'll follow this. And we see we're returning EAX, which is our resolved API address. So let's just verify this by context, like we did previously. So select the function, hit Control-Shift-F for cross-references. And I'm just going to pick one of these in the middle. And you can see here, this is the all-in function 41360, called a whole bunch of times. Let's just click this. And that context actually even gives us a little bit more context, and we'll see it in action in a second. Let Ghidra regraph. So let's hit L to label, and we'll call this get proc address by hash. So we see we're calling get proc address a whole bunch of times. We're passing in as the second argument a hash value. and it's a different hash value each time. The return result is getting stored in ECX, which comes from the same global variable, and then it's offset by a different offset each time. That basically means we're building our temporary import address table, and then we'll later call those. So you can see if you saw this just in code, anytime you see a big string of the same function called, the return stored into a structure, and a kind of hash value passed in, you're almost always doing a get proc address by hash. So pretty simple to see by context, pretty simple to see by instructions when you're used to it. And that's really all we need to talk about to go over these examples. So again, in this case, we didn't resolve what these hashes are, but in the next video, we'll go over a methodology to use a debugger and a scripting language to kind of get the best of both worlds without needing a lot of experience and without having a dirty database. So that's all we need to talk about today. So I hope you enjoyed the topic today. If you did, please like the video and subscribe to my channel so you get notified when new videos come out. If you want more malware analysis tips, follow me on Twitter. And if you're interested in more structured training, check out my website for the malware analysis courses I have. And until next time, keep on practicing and try to learn something new every day.